Alright, welcome to another Mathcast. In this episode, we're going to be taking a look at the method of isonclines. I have a differential equation up here in the left-hand corner of the screen, and I also have an axis that we're going to be filling in our information. So basically what we're going to be doing in this episode is what I discussed in the last video, something called the method of isonclines. Now, in order to apply this method, and if you need a refresher, go back and view the previous episode. In order to apply this method, I have to write the differential equation in standard form. So in order to do that, I'm going to get my dy dx here on one side, and I'm going to write this as minus x over y once everything is over to the other side. So this minus x over y is what we called f of xy in the previous video. It is basically the function that controls the slopes in the slope field that we're trying to sketch by hand here. So rather than go in at each and every point and calculate the value of this function to find the slope, we're going to create an isocline. And remember, the isoclines are always of the form f of xy equals c for some value of c. Now, it's always a good idea to start with the value c equal to 0. So I'm going to create a table of sorts here, and for each value of 0, I'm going to figure out what the isocline looks like and then plot it over here on the graph. So c equal to 0 corresponds to negative x over y equal to 0. I'm plugging in c equal to 0 and f of xy is negative x over y. And that corresponds to, if I multiply y on both sides, corresponds to x being 0. Now, x equal to 0 is the x-axis. So this is a vertical line. And so let me draw in the vertical line. I'll do my isoclines in, let's say, green here. Drawing a vertical line, there's my isocline corresponding to c equal to 0. Now, the c equal to 0 isocline is a very important isocline. It's called the nullcline. We'll talk more about nullclines later in the semester, but this is a good start. All right, let's try another isocline. Once we have our isocline in place, you should probably get in the habit of drawing in a couple of line elements. Everywhere along this line, things have slope 0. So draw arrows that indicate slope 0. Now I could spread them apart a little bit more than this, but just trying to be complete. Now the question is, do I know which direction the arrows are going to point? Because they could be pointing in either direction here. But we'll talk about that here in a second. So there's my isocline. I know things in the plane are neither increasing nor decreasing along the x-axis. They have slope 0. All right, let's try another slope. Let's do slope of 1. So the things that have a slope of 1 lie along a line that looks like this. If I put it in sort of a standard form for lines here, then this will be the line y equals negative x. So let me go ahead and graph that one. Y equals negative x would be from here through the axis all the way to the other side. So this is the line y equals negative x. It corresponds to a slope of 1. Now you have to divorce the idea of the isocline from what's going on in the plane. In the slope field, everything on this line has slope 1, even though the line itself has slope negative 1. So the line doesn't tell you anything about the slope of the line has nothing to do with the slope field. You know that along the line, things in the slope field have slope 1, though. So slope 1, I just want to draw in line elements that are at least somewhat close to having slope 1. So something like this. And I'll space these out a little bit more. So everything along this line has slope 1. All right, let's do another one. C equal to -1. I think you can see how this one's going to turn out. This is the line y equals x, so we're going in the opposite direction this time. So we're going through the origin up to the other side. So this is the line y equals x, but it corresponds to things having slope -1. And so everything along this line has slope -1. All right, let's do maybe one more here. How about c equal to infinity? Now, like the null line c equal to 0, it's usually a good idea to always do c equal to infinity as well. C equal to infinity would be -x over y equals infinity, which the only way that that would happen, well, there's two ways that would happen. X could be infinity, but that's kind of weird. We don't want to go all the way out to plus or minus infinity along the x-axis. Or what you notice is that that's possible if y is equal to 0, which is the horizontal axis. So anywhere along the curve y equal to 0, anywhere along that horizontal axis, things have infinite slope. Infinite slope, all that's going to mean is that you have vertical arrows. Essentially, the slope is undefined at these points. Later on, when we talk about existence and uniqueness of differential equations, places where the slope is undefined in a plane will be of special importance. And so the idea here is we have these elements that are vertical lines. Now, understand that the way that we have the arrows drawn in here, the actual arrows themselves aren't going to point in that direction. If you see things coming from this direction, they're going to point down here, and they're going to point up here. So things will be coming in vertical from both the top and the bottom. It's sort of weird. What it means is that solutions want to get close to the line y equals 0, but the closer they get to them, the more vertical it becomes, and the less the differential equation can actually inform the solutions of where they're supposed to go. The slopes become undefined, so the differential equation loses properties of uniqueness and existence at that point. However, if you start on that line, then you can stay on that line. All right, so now it's time to think about what solutions might look like. And based on the isoclines that we have, let's just pick a starting point here. How about y at 0 equal to 8? It looks like solutions here would do something like this going forward and this going backwards. And if you sit and stare at it long enough, you can see that solutions here are going to be concentric circles. Now, how could we verify this? Well, one of the techniques we're going to use in a later video is a technique called separation of variables. And so if you're trying to solve a problem via separation of variables, it turns into a calculus problem. And so we'll take this dy dx equals minus x over y. And we'll separate out variables here, multiplying all the y's on one side, getting all the x's on the other. And then we'll integrate both sides. We're just treating it as a calculus problem. And then after we do that, we get y squared over 2 plus x squared over 2 equals. Now, both of these are going to produce a constant of integration, which we'll call c. And notice if I multiply through by 2, I get y squared plus x squared equals 2c. But c is an arbitrary constant, so there is absolutely no reason why I can't rename it. And I'm going to rename it r squared for obvious reasons. This says that all solutions to this differential equation are circles centered at the origin. And our little sketch of the isoclines allowed us to basically figure that out. Now, this technique is one of those that you're not going to want to do this a lot this semester. Once I teach you how to do slope fields in Maple, harder slope fields are going to be much more difficult to do this method for. But for easier slope fields like this, you can readily see how the slope field matches up with the solution to the differential equation. And really the important thing to get out of this is this idea of isoclines, level curves, and nullclines. And so you're really going to want to pay attention to this part of the problem. All right. Thank you for watching.